Introduce himself and set himself up.
Thank you, Dr. Davis.
How's everybody doing? I mean, it's Thursday night, right? And it's econometrics. Where else would you rather be now, right? So good stuff. So first and foremost, thank you, Dr. Davis, for allowing me to kind of come in and talk about, really we're going to talk about regression today. So I think in your previous courses, we probably should record though, right, Dr. Davis?
It's recorded.
Is it? All right, cool. And I believe you were chapter 4 and chapter 5 before they got to this course, somewhere around there. So we're words like linear regression and regression in general and coefficients. Hopefully that rings a bell. If not, that's okay, because we're going to talk about some of those elements today. But we're going to really focus on kind of multiple regression, and then we'll do a little bit of work in R. So I think, as Dr. Davis just alluded to, it sounds like you're working on some sort of project where you're going to pull data into R. R is a very unique statistical platform, and as I'm sure you're aware, there's other statistical platforms out there. I'm sure you've heard of SPSS, Stata, and then R is generally acceptable in the community because it's free, right? So the other ones kind of require a licensing fee. So pretty popular. So again, my name is Mike Feldman. I'm currently a doctoral student, DBA 7. So I think I'm almost, a year into my program-ish, heading into my second year. So been a pretty exciting program thus far, to say the least. So I'll talk a little bit about my background, but in the beginning of this block of instruction, I kind of want to make the connection between kind of industry and academia, right? So I don't come from an academic background per se. I come from an industry background, a military background. So I kind of want to walk through some of that and kind of what I do here in the city of Jacksonville, to connect the dots to kind of what you're going to be learning here in class. So oftentimes, just like in high school or in college or in some of your other classes, typically we try to understand how we can apply that when we get into the industry, right? And sometimes that's usually not applicable depending on where you go and what kind of job you take on. But what I can tell you is everything that you're learning in this class in my world is 100% applicable. I have an army of interns over the summer that were doing a lot of this work, and I'm going to show you some of that here shortly. So again, thank you, Dr. Davis, for inviting me here this evening, and I hope you guys find this class a little bit engaging as well. And it's important stuff, so I think you'll enjoy it. So without further ado, we'll go ahead and move forward. So who's this guy that came into your class today to talk about multiple regression, right? One of the most exciting topics known. So I currently work at the Jacksonville Transportation Authority. Everybody know who the JTA is or what we do, right? So we run fixed route service. We have an automated people mover that services the north and south bank of Jacksonville. It's kind of like a Skyway monorail system. It's a free service. We have obviously our fixed route bus service, some paratransit that services the ADA community. But what I do is more so on the R&D side. So I specialize in autonomous vehicles and autonomous vehicle technology. So I'm the Assistant Vice President of Automation and Innovation for the authority. So what I'm working on right now is a program called the Ultimate Urban Circulator. Essentially what we're going to do is introduce the first fully autonomous transportation network into public transportation and commercial revenue service, meaning we're going to charge a fare for the first time in the world. So we've been working on this project for roughly since 2018, and we are moving forward in the design process. So in 2024, it's my expectation that you'll be able to come downtown and get an autonomous vehicle similar to what you would find as a bus per se, but this vehicle will be fully autonomous. So that's kind of my world. Prior to the JTA, I spent about 5 years at Amazon, so I specialized in Amazon robotics. So in the fulfillment center, so for those of you that play in the supply chain space, the robotics and automation is a big deal now, as you can imagine, right, from an efficiency and a productivity perspective. So I specialize in North America for deploying the robots in those sites. And then furthermore, worked on standing up the Amazon logistics last mile side of the business worldwide as well, which is, how do we get the package to your house, within an hour or same day. Spent about close to 8-9 years in the military as a military intelligence officer. So did a lot of fun and unique things there prior to that. And then as far as schooling goes, I did go to the mighty Florida State University. Their football team is not doing well, but I do claim them. I did get my master's in criminology as well from the University of South Florida, and then figured out real soon that criminology and business don't necessarily mean the same thing. So I went to the University of Tennessee and got my MBA, and now I'm here currently working on my doctorate in business administration at JU. So that's kind of my path, and the reason why I want to show that, it's a very non-traditional path to kind of where I am in terms of the industry. And I say that to say is everything that you're learning, believe it or not, is applicable, and is very applicable in my world. So I talked just briefly kind of about like our project. And essentially what you see here is kind of a 3-mile fixed route service. So that'll be the first 3-mile fully autonomous transportation network in the world. So we will do that right here in your backyard in Jacksonville, Florida. And then this is just really a high-level overview of the program that we're not going to get into. So here I wanted to show a quick video. We were just traveling in Germany last week at ITS World Congress, and we gave a few presentations on our program. So on a global scale, there's a lot of visibility on what we're doing here in Jacksonville. So I think this video is going to show you real briefly about some of the autonomous vehicle platforms that we have currently here in downtown Jacksonville. Parallel to what we do in our day jobs, we run a fully operational testing facility right here next to the airport. So what you see here, fully autonomous vehicles running around Mayo Clinic carrying samples with no driver on board. So we do some pretty cool stuff here in Jacksonville in your backyard. Who would have thought? We also have a strong partnership with FSCJ. So I'm sure you know what FSCJ is. We operate high-speed autonomous testing on their CDL track. So that's what you see here. Fully street legal, fully autonomous, fully electric, and driving around. So that's currently our fleet, and those are fully autonomous. And this is our downtown headquarters. So for those of you that travel downtown, that's where I work primarily. So just a brief introduction there. So let's just go ahead and jump right in, shall we? All right, so today's topic, again, just to kind of circle back, is build on kind of some of the regression conversations that you've had thus far, kind of building on that linear regression and kind of understanding the unique characteristics between, one unique dependent variable and one unique independent variable. And how do we grow that and expand that theory, if you will, and looking at multiple independent variables and how we can look at predicting kind of the outcomes of those dependent variables. So just to circle back, kind of the first, really the phase of this block of instruction. So we'll start with this opening vignette. So this is really going to set kind of the context of how we kind of lean forward with regards to thinking kind of in a linear context to a use case or a problem as you're just looking at in your background. To kind of somewhat of a more of how do I look at the other variables that I may not understand today that also might influence the outcome or the output, i.e. your dependent variable. So let's start. So although school districts with lower student to teacher ratios tend to have higher test scores in the California data set, so the CA data set is something that you can pull into R. Perhaps students from districts with small classes, right, we're talking about class size, have other advantages that help them perform well on standardized tests, right? So what do we mean here? When we talk about, other advantages, right, we're talking about other unique variables that might impact our outcome, right? And those are really independent variables in context. So omitted factors, such as student characteristics, can in fact make the estimates from linear regression misleading, right? So sometimes there are these other things, right? These other characteristics, these other variables, if you will, that if we don't take them into consideration, that single linear model then becomes a bit robust, right? And we don't truly understand the interaction between the dependent variable if we're not kind of carving out some of those additional variables that might impact that estimate. So as we think about kind of this vignette and we think about this ideology that there are other things that could impact our output in our model, right? We sometimes have to think of this bias, right? An omitted variable bias. So as I mentioned kind of at the top of the block was you guys are doing some work in chapter 4 and 5. So hopefully this is not too foreign to you. But just in case and kind of to recalibrate, the previous analysis of the relationship between test scores and class size discussed in chapter 4 and 5 has a major flaw. We ignored, right, other determinants, right, i.e. those other variables that could impact your output for test score that correlate to the regressor class size, right? So we're really taking kind of this variable and we're regressing it against something to understand if we can truly predict with confidence what that output would be, right? That's the whole point of regression. So in statistics, this omitted variable bias, these things that I've omitted tend to compensate within the model. So in order to truly understand and offset that bias, we have to think of some of the other characteristics, right? Or some of the other independent variables that might drive this relationship. So the key takeaway here is the bias results in the model attributing the effect of the missing variables to those that were included. So it's important as you get underway in some of your research, right? It's very important that you understand all of the different constructs, the latent constructs, and you kind of assign all of these different items to them. And then you do a survey, and really collecting all that data is going to allow you to understand what those unique relationships are. So that's really the whole point of this exercise. So then, as of course, there's no block of instruction without a fancy equation that looks like it's in a different language, right? So we talk about this idea of linear regression, right? Can somebody tell me what we've learned thus far? What is linear regression? Anybody? Online, in the class? Linear. What is linear regression? Because we can't talk about multiple regression if we can't get past linear regression, right? So what makes it linear? What's a linear relationship? Sure.
A straight line.
Straight line, right? So I'm really kind of measuring this relationship of an independent variable, right? And how I might be able to predict the outcome of a what? Dependent variable, right? Simple relationships. But then I say, you know what? We go back to kind of this omitted variable bias and we say, hey, we do understand that there could be, right, more elements, more variables that could impact outside that one single variable I looked in that linear, that straight line relationship. So how does that affect the model, right? So to do that, instead of running some of those linear regression models and looking at the relationship between A and B, we then take it a step further and look at a multiple regression, which you can imagine means what? We're looking at multiple things, right? Multiple independent variables. Because we believe that these characteristics will influence the model in some way, right? In some way. Do we know what way that is until we run some sort of statistical model? No, right? We collect our data, we introduce it into a regression model, and we run the regression similar to what we're doing R today to truly understand what the effects of these variables are on your dependent variable. So let's talk about this equation. So we see y1 equals, right? So I'm sure hopefully everybody understands what we're referring to when we say y. Excuse me, yi. What's the y typically stand for in a statistical relationship? It's a dependent variable, right? Right? It's the thing we're trying to understand how we can use other things to predict what will happen. Okay? So this is the thing we're trying to measure. Okay? Another good way to say this is represents the what? It's the outcome, right? It's the output. Okay? So in order to understand how we can affect the outcome, we introduce these other things called independent variables, right? To measure the relationship on how the dependent variable is affected. So then you kind of see this B underscore, right? 0 or O. What does that tell us? Sometimes you'll see this in a relationship, right? Sometimes you'll see this as an intercept. But what this really tells us is the expected mean value, right, of y, when all other x values are equal to 0, right? So you'll typically see this in the forefront of the equation, right? You can always expect to see that. Now, are we typically doing this in manual? Well, in one of my statistics class, yes, we did. It was very painful. But do we have now platforms and technology at our fingertips, such as R, to actually execute this transaction for us? Yeah, we're going to do that today. But it's important to understand the foundation, right, and the fundamental characteristics of why these things happen. Okay? So then we have X1. We kind of already hinted here, and you kind of see this logical flow, right? X1, X2, X3. What are we talking about? What do you think we're talking about? We said that y is our dependent variable, right? So what do we think the x's are? Sir? Independent variables, right? So here we're starting to layer in some of those different constructs or variables, right? That we believe is going to affect what? Right? The outcome, right? Our dependent variable. Good. So we talk about that B1 and B2, right? The estimated regression coefficients, right? So when we see a change in y, right, relative to 1 unit change in one of these x's, holding all of the other independent variables constant, that's what we're saying here. That's what we're saying by this description. And then here you see kind of a consolidation procedure at the end. So don't focus too much on that. So K is kind of the total number of regressors. That's what the subscript is here. So again, just to circle back, it's important to understand mathematically how to solve this equation, right? Back in the day, there was no SPSS, no Stata, no quantitative kind of software. So we were writing this. Good statistics class will actually have you go through this exercise so you understand the fundamentals that we kind of walk through. It's very painful, right? But then you understand truly the foundation. So when you go to apply this, right, within your statistical processing software, you have a pretty good understanding, even though you're not manually calculating, but the output you start to understand, right? Because you understand the elements of the equation. Okay? So I'm going to take a quick pause if there's any questions before we proceed. Everybody good so far? Yeah? We falling asleep? Do we need to stand up and do some claps? No? I'm just, all right, just making sure. Because this stuff can be interesting. We'll use that verb. All right? But we're trying to make it fun. All right, so we talked about this linear relationship, right? A to B. We talked about this multiple relationship where we add all these other variables to understand what their impact is. So we talked about coefficients just briefly. So there's a lot of stuff on this slide, right, that can be somewhat difficult to decipher. So let me help you. So I'm going to read it to you, and then I'm going to kind of walk through it kind of in layman terms, right? So beta slope. So what are we referring to when we say slope, right? Slope of a line. Easiest way to explain that. So what we're really trying to hear is rather simple if you think about it within the given context that's shown you. So beta slope coefficients are different in multiple regression. The predicted difference in y between two observations with a unit difference in x1 holding x2 constant, right? So we're trying to measure those kind of independent relationships. Another term used is the partial effect of beta 1 on y being what? There you go, which is typically our dependent variable, right? And x1 or x2, which is our independent variables, right, in our regression model, right? So what we're trying to understand here, again, is what I said is pretty simple. That beta coefficient is a value that helps us understand what that strength is, right? Because what we're really interested is in the strength in the relationship. It's one thing to say it's significant. I'm sure you guys understand that, right? P-value, 95% confident. But we really want to understand what the true effect of that relationship is. So we measure that as a form of strength of each independent variable on that dependent variable, right? We truly want to understand the strength and the significance of each one of those x1s, x2s, x3 when we regress them against our output variable, which is our dependent variable. Okay? So here we go. So we talk about this idea of fit, right? And measures of fit. When we're talking of measures of fit, think about a line, right? And you went out and collected a bunch of different data, right? You went out, you deployed a survey, you felt like a hero because you got 300, observations, which is great. I've learned. And you're trying to understand kind of how those data points fit across a line, right? And we'll call that line a regression line. So we have this interesting acronym that you see here, SER. Who knows what SER stands for? Have you guys learned that yet in chapter 4 or chapter 5? Standard error of regression, ring a bell? Standard errors, estimates, are those any of those keywords ringing a bell? Yeah, maybe, kind of. All right. Well, let's walk through it anyway. This really these standard errors of a regression, they just tell us how wrong the regression model is, right? What we're trying to understand is the distance between the data points once we plot them in the regression line. So just imagine we have a regression line with some sort of slope, whether a positive correlation or a negative correlation. And what we're trying to understand is when we plot all of our different data points against that line, there's the distance. It's never going to be a perfect fit, right? I mean, it may happen, I guess, in unique circumstances, but typically you're going to see this homoscedasticity or heteroscedasticity, right? You're going to see this dispersion relationship of all your different data points along the line, right? They're going to be somewhere on that line. Have you done the scatter plots yet? Have you guys done any scatter plots? Right? You're going to see that, right? They don't usually match up, but they show you some sort of relationship. So that's what we're talking about. So when we look at the standard error of regression, we can also look at the distance or the estimates between those data points in your regression line. And there's also a manual way to do that, which is also very painful, right? So we can do those types of things. But it's important because you're trying to understand the overall fit to your model, right? All right, so here we go. So what is R? Not as in R statistical software. That was the $100 question of the evening, right? R, just R in general, right? So let's walk through it because you've got this idea of R squared, right? Have you guys done R squared yet in any of your work? No?
Yes.
Yeah? So good. Tell me about R squared. That's the follow-up. You knew that one was coming, right? Right? So like, yeah, we talked about it. Yeah, I read it in a book one time. Got it. Okay? But R squared. Think about that linear relationship. Yes, ma'am.
It measures how good the fit of the model is.
Good. Right? How closely they fit to that line. Right? Hence, it's why we call it a measure of fit. Right? So we're very good. So we have this kind of R squared and then this other thing called an adjusted R squared. I think in not only in econometrics and statistics, I mean, this could be adjusted R cubed, right? We'll keep going forever, right? But we're going to sit here and talk about R squared. So if we look at R squared, and as the young lady mentioned, it's a measure of fit that indicates how much variation of the dependent variable is explained by that independent variable, right? But typically we look at R squared to measure the relationship with what type of regression model. So we're only looking at usually typically one independent variable and one dependent variable to understand that relationship. So by definition, that would be what? Linear regression model, right? Simple. But what happens is that, you know, we look at that as kind of a percentage, right? And so that's how it's measured. So when you do an output in some of your statistical modeling, it'll give you a percentage so you can understand. But what happens if we have more independent variables? Right? We gotta make an adjustment, right? Because we no longer have this kind of linear relationship that's under investigation. And we've introduced a whole bunch of other things into the model. So I've got to adjust for that, right? So what kind of R squared is that? That's what I'm talking about. All right, good, right? So that gets us to adjusted R squared, okay? And these are, you're going to see these because I know Dr. Davis showed you kind of some of the descriptive statistics and ANOVAs and t-tests, and we'll look at some of that stuff today. But this becomes a very important metric, very important output. So you'll want to take note of this because this is very important. Because what we're trying to do is explain really variation, right? We want to be able to explain to a certain percentage or to a certain level of detail the variation that we can explain in terms of predicting that output, right? So I may have 5 different independent variables, right? X1, X2, X3, X4, X5, right? But what I'm trying to explain is the percent of variance on how I can predict the output, right? That dependent variable. So those will not be analogous. Those will not be the same. So in order to do that and account for the new variables into the model, I've got to adjust that R squared, right? And this is exactly what it says for each regressor. And by regressor, I mean what? Those additional independent variables. So we keep it clean. Everybody good so far? Okay? Perfect. Our favorite friends, right? Formulas. We love them. You see them everywhere. What's also unique about formulas is if you Google a formula, you'll find 17 different versions of that formula. But essentially what we're saying is all the same here. So let's talk about, again, the fundamentals. Are you going to calculate this manually? Most likely. No, but if you go to DBA school, yes, you will. So that's why I show it to you. So N is simple, right? N means what? Number of observations, right? Your sample, right? It's my number of observations. I put out a survey and I set a threshold of 200. I got 200. So N equals what in this case? Very good. So K is the number of independent regressors. So you will see if you look in a variety of different models or books or articles, this may be oftentimes referred to as a predictor, right? So you may say P here instead of K as a kilo. Again, everything means the same here. And then SSR, sum of squares, that's sum of squares due to the regression, right? Due to regression. And then you have your total of sum squares. We're not going to get into that. I don't think that's part of this block. But really it's just understanding kind of if you were to calculate this manually, now that you have kind of the template, you could essentially plug the numbers in there and achieve an adjusted R squared without a statistical platform. Okay? Any questions so far? Do we need a water break? No? Is that exciting? Perfect. All right, so then they got this thing called multicollinearity. That's a huge word because it ends in a Y, right? So any word that ends in a Y is going to be problematic for us, right? No? Joke didn't go over well. That's okay. All right, so let's talk about multicollinearity, right? There's a lot of text on the slide, but just think about it. Multi, right? We're talking about what? Multiple regression, right? So anytime I talk about multiple things, I introduce kind of this opportunity, right? And this opportunity that we're defining here from a multicollinearity perspective is what? I've got all these independent variables, right? But what could happen sometimes is that we may see some very strong relationships between what? The independent variables, right? So if I have x1, x2, x3, x4, x5, sometimes those independent variables, even though we're trying to measure each one of those unique independent variables and kind of how we can predict the outcome, which is our dependent variable, sometimes they overshadow each other or they're related to each other. And what do you think happens when we see that? Problems, right? Simple. We have problems now with our model. So then we have to figure out a way to offset some of those problems. So multicollinearity, there are ways to test for that. So would you be able to see that manually? Not necessarily, but if you run a script in R as an example, or you use some sort of statistical platform, there are certain tests to test to see whether you have a multicollinearity issue. Okay, long word, ends with a Y. In layman's terms, we're trying to understand if the independent variables are related to each other. Everybody good so far? Okay, not a super complex, but it could be a problem. Because if you don't catch it and you don't adjust for it and you don't run the statistical test, your results, everything is going to be impacted. There's a lot of second and third order effects. So you've got to take a look at that. Okay? So how do we deal with it? That's the more, right? It's like, okay, got it. My independent variables, there's some issues that are related to each other. It's strong, right? I got a problem. First step is understanding you got a problem, right? Second step is, okay, well, how do we deal with this problem? So what do you think are some ways? Is this the first time you may have heard of multicollinearity, just to check? Or have you guys covered this thus far as well? Seem familiar, vaguely? No? All right, cool. So we got to deal with it, right? We got to do something about it. So the first thing we could do is remove some of those highly correlated independent variables, right? We could pull them out of our model if that's necessary, right? To lean the model back out and reduce that overall collinearity. We could also look at, depending on how strongly they are correlated, we could combine them, right, into one independent variable and absorb some of that collinearity. But we could also do some advanced techniques, such as principal components analysis or partial least squares regression, because we've understood that there's this interesting relationship of, or this interesting idea of collinearity. So now I've got to figure out if there's another statistical approach that I can compensate for that collinearity. Hence partial least squares regression. So it's another form. There's ordinary least squares, there's partial least, there's general, there's about 17, I think, different types of regression, right? So I say that to say there are ways to deal with these problems. So if you see it, it's not a big deal. There's ways to deal with it statistically. Everybody good so far? You sure? Any questions? Anybody want to add anything? Dr. Davis, anybody?
I'm not going to learn POS or
Not in here?
or BCA.
Okay, cool. So we're going to do convolutional neural networks though tonight, right?
No, that's
No, yeah. All right. So just understand that there's this relationship that could happen, right? We recognize it, and we do that through statistical modeling, just like everything else. And then we got to take a look, right? We got to figure out how we're going to address it, because it's going to impact your model, it's going to impact your results. And when you write results, everybody's going to see that you have a problem with collinearity, because you're going to show us a table of your statistics, and we're going to see it. So that's how it works, right? But easy stuff to understand. So then you have this idea of imperfect multicollinearity. So just take a second to kind of read what you see before you. I don't think we're going to get too much into here, because we talk about ordinary least squares, estimators, and a little bit kind of more advanced techniques. And what I really want you to take away, right, the take-home message from this is that there's this thing out there called collinearity, right, that ends in a Y, that we need to understand, and we also need to deal with it. So this is kind of a kind of inverse reaction to a perfect collinearity or collinear relationship, hence the word imperfect. So just take a second, read that. I think Dr. Davis will make the slides available to you. Maybe something that you want to, investigate further when you have time. But we can't ignore it, right? And that's the point, right? We cannot ignore it. All right. Awesome. I know I think we're, 40 minutes in, Dr. Davis? Maybe we take a 3 to 5 minute water break. Does that work for everybody? And then because I want everybody to come back, kind of load up R, because we're going to get into some exercises and kind of take what we learned kind of in this first block of instruction and apply it, right? And everything's going to really make sense here shortly. So maybe we just reset 3 to 5 minutes. I got the time now. We'll call it 40. So we'll just return between 43 and 45. And then please have our studio up and ready to rock and roll. Sound good? And then for the folks online, hopefully you guys heard that. I'm looking up as if you're up there in the cloud, but hopefully you guys heard me online. We're going to take a 5-minute break, folks. When we come back, the expectation is you have our studio up, and we're going to take what we've learned thus far in the first block of instruction and do some application here. So we'll see everybody back at 6:45. Pull up R here. This photo. There, should be okay. Try to go here. Everybody has our studio downloaded, right? Like you guys are all. If not, in the next 5 minutes, can you download? Here?
Yeah, I'll just X out all of them at the top. Oh yeah, you can just delete that one.
That'll work. Then everybody will need to do names, so we'll start there. I think nobody can draw a perfect bell curve. That's evidence that I cannot either.
Should we draw it on the other board and make it show? On
Yeah, that'll be good.
on this side.
And then,
Let me see. There you go. So it's
sharing video now, they can see that section of the board. Oh, perfect. Thank you. All right. So just going to check the old chat room here. Do you need an intern? So I am always looking for interns. Can you turn on the camera so we can see you? Oh,
You already did.
can you guys see me now? Famous last words. Turn on the camera, sir. Can you guys? All right.
Yep.
6:39. Perfect.
Yep. That's
All right. So hello, Kathy and Catherine. Okay. Mr. Root, I will make sure, Dr. Davis, I can I can attach my information. Maybe you could just put it in Blackboard. And then Quentin, great question. Autonomous and electric? Yes and yes. I'm not interested in anything that uses your standard propulsion or combustion engines. So no gas, no alternative fuels, no CNG, all electric. I'm very interested in studying hydrogen right now as well. That song got me ready for war. Let's code. That's what I'm talking about. Joyce with an emoji. What is that, Joyce? I'm not hip on the emoji cons yet. All right. Joyce is still on break. Post your email so I can send you my resume. You got it. There you go. Under the cover of Zachary Davis. All All right, we ready to rock and roll? We ready to have some excitement? We ready? Yeah, everybody logged into RStudio? Yeah, everybody got it pulled up? All right, so let's make some statistical magic happen here. So it's important that we, take what we learn in these fun lectures, right? Because those can sometimes be boring. But when we apply it, right, when we apply what we learn, that's when it starts to make sense. So we're going to use some high-level vignettes, kind of use cases, some problems to address. That's going to kind of reinforce some of the things that we've learned thus far. All right, so we ready, everybody online? Because we're going to need to follow along because we're going to kind of code real time. So everybody good online? Can you guys see me now? I'm assuming the noise is confirmation. Thumbs up.
Gotcha.
Yeah, that's what I'm talking about. All right. So everybody go down into your console, bottom left corner, right? We've got 4 quadrants. So again, to calibrate you again, you've got kind of your coding up in the top left quadrant, where we'll do our coding work, right? And below that, you have your console, your terminal, and your job. So you spend some time in the console. The console kind of reinforces what we're actually putting in from a code perspective, up in the top left, right? So we'll see kind of the reflection of those results in the bottom, naturally. Then you have the environment. So I think you, sir, were talking about kind of the environment. And I know that's, I think, part of your class project as well. So you'll see your values, your variables, right? Those will show up over here. So anytime we do some sort of coding or we pull in data sets, right? You notice when we pull in data sets, we're going to pull in Boston. We're going to name them some things. So you're going to see that where? Over here, right? In your environment. And then to the bottom right, if we do any sort of, some scatter plotting, we do some regression, then we want to look at kind of how our data is lining up against a regression line. And we actually code it to do that. We'll see that down here, right? So anybody done a scatter plot yet in R, right? Shows up where? Down here. All right. Everybody's good? All right, let's rock and roll. So bottom left, everybody type in names. So you guys see the bottom left. I think you guys do this every time, right? Yeah? All right, so names, and then for the folks online, sys.info, and then make sure you pay special attention to the parentheses, of course. Just a recommendation for playing in R. A lot of us like to type fast, right? Like it's a race. But sometimes racing in R is a bad thing. It just creates more problems, right? Because sometimes we miss a character. So my personal preference is to populate. So I will type in names, and then I'll let the system populate all the different options for names, right? And then I'll scroll through there. I'll take my time. So slow is smooth, and smooth is fast, right? Especially when playing in R. It'll save you a lot of time. All right. Everybody in the class, good? All right. So you see in your global environment, you should see what I see, right? 1:8. Everybody's good so far. Online, folks, you good? All right, so here we go. So I want to just pop back into the PowerPoint real quick so I can just share the use case with you, okay? So here's the exercise. So we're going to pull in kind of this Boston housing data set. That's going to be one of the first things we do, right? Because we want to take a look at it. So I'm just going to read from the slide, all right, just to get everybody on the same sheet of music. So we're going to work with Boston, the Boston housing data set, which contains 506 observations. So we're going to just kind of do some checks to make sure that it lines up with what we're seeing here inside of R. On housing values in the suburbs of Boston. Anybody from Boston? All right, good, because it's cold up there. And the Red Sox, are they any good? No? All right, perfect. Anybody a Devil Rays fan? I'm from Tampa Brady. No? All right. Looks like I'm all alone by myself. All right, so Boston comes with package mass, right? So we'll introduce, there's this package, there's additional data that's baked into there. Which is always installed for the interactive R exercise below. So when you pull this in, we're going to pull it into R, and it's going to be positioned there for you. So we're going to load both the package and the data set. We're going to walk through the code very methodically and do that, make sure everybody's good to go. And then we're going to get an overview of the data using the functions known from the previous chapters, right? So we're going to look at summary functions, right? Coefficients, your standard stuff that I'm sure you guys are all 100% ready to talk about. But if not, that's why I'm here. So we'll be in good shape. So we're going to estimate a simple linear regression, and that is a relationship between Is it a lot of variables, a couple variables? You guys got to help me out here. There you go. All right, so we're going to take a simple linear relationship. We're going to regress something on housing. I think in this case, it's socioeconomic status. So we're going to see if there's a relationship between socioeconomic status and median home values. Pretty simple. That's why we call it a simple linear regression. And then we're going to save it, right? So we're going to run the model, and then we're going to save it, and we're going to assign it a name, which will be VH_mod. So we'll do that together. And then we're going to print a coefficient summary, right? So we're going to take this model, and then we're going to plug into R and tell R to run a summary, right? So we can see everything in our console. So pretty simple stuff. And then it's going to report robust standard errors. We're going to tell it to do that. And then we're going to talk about kind of what those responses look like. All right, when I say we, that means you. All right, so you're going to tell us kind of what you're thinking, and we'll just walk through those, right? Okay. All right, so we ready to go back to R? All right, we're going anyway. So here we go. Let's jump back into R. So here we are. And I'm going to do some things along the way that I like to do. You do whatever you want, of course, just as long as you run the code correctly. But it's very important to organize yourself. So you'll see as you enter multiple lines of code, it's hard to go back and like kind of reference sometimes what you were trying to do if you don't put notes. So do you guys put notes in R? Did you learn that? If not, I'm going to show you guys how to do it. It's super simple. All right. So here we go. So now we're going to attach both packages and load the data sets, right? That was like one of the first ingredients to this puzzle. All right, so here we go. So we need to bring it in from the library, right? All right, so here we go. So everybody type library, right? And see how we get kind of a population of the different library items. I always click it. You don't have to do that, but I get it right the first time. So library, and we're going to bring in AER. Okay? Everybody good? Then we're going to go down, and we're going to also bring in library mass, right? Because we said we wanted to bring in that data along with AER. So we're going to do library again. Okay? Library, and then we're going to go mass, right? Bring in that as well. Okay? So then we also want to bring in the housing data, right? And we're looking for this particular use case is where? Boston, right? We talked about the Boston. So we gotta bring that in here, right? So how do we do that, right? So it's data. So our first line of code is what? Data, right? Just regular data. I'm going to click on it here. And then here we got to put quotations around it, right? Everybody remember that? So we're going to go quotation here and see how it populates both because it's data. It knows it, right? It's going to give us that prompt. And then now we're going to go Boston. Okay? So there's a couple things we can do here. You can click on the one and you can run this, right? So let's just go ahead and do that before we get ahead of ourselves. So you can click one and highlight. You can highlight multiple items, but we'll keep it simple. Okay? And everybody see what's happening down here in the console? Red is not always an error. It's not always a bad thing, right? It just means we're just pulling in the data. It's going to be okay. Everybody good with pulling in the library, AER? So let's go down here. Let's go to mass. Let's run that. Okay. Was that a comment online? Let me pull up the chat. And then for those in class and online, whoops, go ahead and run Boston, okay? Whoops. And we'll run that. All right. And then you should see Boston shift, right? You guys see that? Boston shifted over to your values. So let me jump in and you got it? All right. What was the?
It was just, he said he's not getting that time, so he didn't install the package.
Okay. Are you good to go online? All right. So here's what I want everybody to do here. So go ahead and give yourself some space. You guys see what I just did? I just gave myself some space. Doesn't affect your code at all. All right, but let's go ahead and just put some notes. Because if you say when you save this as a .r file and you go back and you're like, what on earth did I do in line 12? Right? This is how you want to keep keep track of this real time. I've made the mistake. Trust me. You probably want to do this. So to do this, you need to turn it to kind of a green text, and all you're going to do is just the number sign. When you put the number sign, you can now type whatever you want. It'll never run it as code, right? So that's kind of like a page break from a code perspective. So here, you can put it below, you can put it above, whatever your preference is. But here, all we did was attach, right? We attached both packages and loaded the data. Right? That's all we did. Right? We pulled it into the library, we moved it over to the Boston, over to the values. So now when we save this file, when you guys hit Control S or you hit this little floppy disk, as if those are a thing anymore, that's going to save your .r file. What I like to do is see where it says Untitled 2. If you don't get into the modus operandi, if you will, of saving that, like right when you start, you'll have Untitled 2, 3, 5, 7, 9, 12, and you'll have no idea what those are. So I always recommend you save that R file initially as assignment 2, assignment 3, assignment 4. So it's easy for you to go back. All right, so everybody's got your console. Console's good. Nobody's seeing any errors. Everything's loading correctly. All right. So here we go. So let's go on to the next step. So we talked about running some summary, right, statistics. We kind of want to see what the data looks like. So oftentimes when you get a data set, you want to poke around and kind of see if there's any anomalies, if there's any missing data, because that can impact your statistical model, right? So let's take a look at that. So to do that, pretty simple, right? Who would have thought it would have been summary, because we want to see a summary, right? It's going to populate, and then always notice it's going to give you kind of that generic definition over here. So if you're wondering which ones you should choose, you'll always see it. So I always click, again, just a good procedure, and we want to look at the Boston data set, right? Because that's what we're interested in. So what are we going to type in between the parentheses? Boston, right? Cool. So we won't need quotations for this because I already pulled it over to the data. Everybody see it in the global environment? Yeah. So see how I only type, so that's another characteristic. If you type just a couple characters, since you've already loaded in your environment, it'll now auto-populate. So it's rare that you'll make a mistake, right, if you choose it from there. All right. So now what we're going to do is let's just run that summary, right? So you can click on the 6, highlight it, and run. And then you're like, holy smokes, right? Holy smokes. This is going to give you a lot of information. All right? Don't be scared. It's not that intimidating. It's just data, numbers, quintiles, quartiles, right? Not a big deal. So here's what you got, right? So you see crime, right? Could be crime. ZN's another variable, right? Now we're starting to see the different variables, right, inside of this data set we call Boston. All right? And then what we've asked it to do is to tell us like mean, median, and max, and we call those. You're going to do those in your project, right? I just saw it on the screen, and that's I think part 3, if I'm not mistaken, which is your descriptive statistics, right? And those generally tell us just general things, right? General themes about the data that you're using. Those are important because that's a good gut check to see, hey, does this data make sense? Does this data set make sense? And that's usually typically where you'll start. So all we did is we said, hey, I want to see a summary of this data. I want to see a summary of the different variables in that data set. That's all this is, okay? And when we say quintiles, quartiles, all we're doing is looking at kind of if we were to separate it into quartiles, right? First, second, third, or fourth quartiles. This is the data that would fall into those quartiles. And I don't think you guys are doing much with quartiles probably in this course. But this function will give you this, okay? So we see we've got age, we've got tax, we've got MEDV, which is the median home value that we'll kind of be interested. And then you've got LSTAT, right? So LSTAT will take a look at that, and that's socioeconomic status. So we'll kind of see if there's kind of this relationship. Can we predict home values based off of socioeconomic status? I think that's a fair question, right? What would you think? What would you think the relationship would be between socioeconomic net status and home values. What's that? Talk to me more about that.
As one goes up, the other one goes up.
Could be. Okay. So she's saying that as socioeconomic status increases, home values increase. What about an inverse relationship? Could we potentially see that?
Yes.
Right? We could see anything. We don't know. And that's, folks, why we're going to do a linear regression model, because that's going to give us the answer, right? Because at the end of the day, data is the new oil. Data gives us the answers. So if we rest on our laurels sometimes in tribal knowledge, but then we bring in this idea of data, then we truly can understand if there's a relationship right there. So that's what we're going to do. Okay? So we're going to check that. We're going to see if there is a positive correlation. We're going to see if there's kind of an inverse relationship. To do that, we're going to have to run what type of model? We've been talking about it, I think, for the last hour. A regression, right? So let's do that. All right, but before we do that, we probably want to put in some notes, right? Just so we can kind of keep track of where we're at. So when you go back and reference, so let's do that. So another thing you can do is you can make an arbitrary line with your pound signs. But for the sake of this, we'll just introduce one. So we're going to talk about what we did over here. So we looked at a summary of this data, right? So we're just going to say something to the effect of obtain a summary of the data set. Boston, right? I mean, that's essentially what we did, right? We took this data set, we pulled it in, and we summarized it by looking at some of the statistics. That's all we did. Everybody good? All right, so the next thing we're going to do is run a regression model, right? So now we need to get a little bit deeper into the modeling to understand whether some of the relationships that you just brought up truly exist. So how do we do that? So here we go. So we'll go ahead and go down one line to make it cleaner. So if you guys want to follow along, then we're going to do our sign, right? And then we're going to introduce the model. So we're going to look at median home value, right, as we reflect on our initial use case, which is that med v variable. Then we've got to use for regression what we call a tilde, right, the key that we never ever use and always wonder what it means. It's in the top left of your keyboard, most likely. Everybody see it? Yep. All right. And then you'll pull in another space. And remember, we want to regress, right? So we're going to look at this relationship between these two things. So that variable for here is going to be LSTAT, which stands for the socioeconomic status. So we'll type in LSTAT and bring that in. Okay? And then we've got to say, okay, we want to regress these things, but what data set are we going to, we're going to pull this information. And we're going to pull it from Boston, right? All right, so we need to tell it to pull it from Boston. So to do that, we tell it we want the data, right? And we want the data to equal, so we'll do this, just an equal sign, and Boston, right? So now we should be able to run this model, okay? So let's have some fun. Let's highlight it. Let's go up to our top right. Unexpected symbol. It's an L. I hit a 1. Very good. All right. So now we said, hey, this is the model that we were telling the system, this is the model we want to run. So now we've got to go to the next step. And that next step is to kind of print the summary, right? We want to summarize what this model is going to look like. So here's what we got to do. So in order to do that, we've got to do, a coefficient test. So, COEF, you'll see it populate here, right? And we just named it this BH_mod, right, which is our model. Everybody with me so far? So we've got to bring that back in. See how it auto-populates here? Should for you. since you already pulled it in and you already ran it. So go ahead and pull that in. Then we're going to do comma vcov, which is the command. And we're going to choose this first option. Everybody see it? Period equals. Go ahead and click on that. And then we're going to do vcov HC. Everybody see it here? HC being heteroskedasticity, right? So let's do that. And we should be able to get rid of some of these here. Okay. So we'll take just a second, make sure everybody gets a line there. So coefficient test in parentheses, VH underscore mod, right? That's our equation that we're trying, or that's the relationship that we're looking to summarize. And then our VCOF procedure. Everybody good? All right.
So we run it that way, like it was the robust standard errors as opposed to the summary function, which is just not correct for the heteroskedasticity.
That's right. And as we mentioned, as part of our initial use case, we want to understand that robustness, right? So in standard, or robustness of standard errors. So this is going to allow us to see that. Everybody good so far? So let's run that. So here we go. Magic happens, right? So all that fun stuff we talked about, that world's largest equation, a lot of words that ended in Y. Here we have at our fingertips now technology to do the work for us. Okay? So who wants to take a stab at this and tell me what this model is telling us? Online folks, feel free to chime in. Okay, let's take a look. So we have a couple things happening here, right? Indicators, right? In terms of what's happening with this relationship. So this is our what? What are we usually going to see over here? Our variables, right? So if I had 5 independent variables, age, crime, sex, gender, whatever it was, right? I would see all of those listed here in a multiple regression, right? But we ran a linear regression, simple regression. So we're only trying to understand how does socioeconomic status impact median home value, right? In the Boston market. So our dependent variable in this case is what? Median home value, right? That MEDV. So if you look up here, so I'm regressing this socioeconomic status. I want to understand if this can predict this relationship, this output, right? How does it affect it? How does that output move when I introduce this variable? What's the relationship, right? So this tells us, I mean, just by looking at it, at our estimate, what are we seeing? I mean, it's a negative number, hint. Just saying. It's not positive, it's negative. Did we get a comment maybe for a response? I heard the thing. Dr. Davis, did somebody post a comment?
Somebody posted the answer to the interpretation, and somebody asked if you can show the console.
So they should see, we're showing the console. Should be sharing the screen that everybody's seeing. Do we need to, it's showing where we're at. Can they not see it?
Only one so they can't pick on the top.
Oh man, it's getting serious in the chat room right now.
Dr. Megan up at,
What's that?
I said Dr. Megan up at the closer to the top now. All those comments have been interprets what the low socioeconomic households.
Perfect, right? So we see this kind of relationship between socioeconomic status decreases, right? When the median home value, what increases? You would kind of expect that. I mean, that seems logical, right? And we've got to do somewhat of a litmus test too, right? Sometimes the data is going to tell us funky things, right? So we have to kind of apply that kind of litmus test, this realism, right? This test, to ensure what we're seeing kind of makes sense. So then we have to say, okay, well, there's this kind of relationship, right? We see it. right? We know it's a kind of a negative, kind of this inverse relationship between the two. You say, okay, got it. But now we need to look at this side of the equation, right? So we see all these asterisks, right? So these asterisks are really telling us the overall strength of the significance, right? So you guys have looked at p-values, right? 0.05, 0.01, 0.001, highly significant, right? Super strong relationships in explaining that relationship. So what are we seeing here? This does a good job. It tells you exactly what in the legend that relationship and the strength of that relationship. So we can explain with a certain level of confidence that if I'm trying to predict the output based on socioeconomic status, the significance level is significant at the 0.001. So I'm really confident that this variable is influencing, right? Or I can predict the output of that dependent variable. Everybody see that? So 0.05. So you see, typically you see the P or the Pearson, P less than 0.05, P less than 0.01, P less than 0.001. So this is going to tell us right out of the gate the strength, right, and the significance. So in this case, it would be highly significant, right?
Because it's showing the 3 asterisks, it's saying it's 0.001.
Yes, sir. Yep, that's exactly right. And that's typically what you'll see in kind of journals, right? Journal articles, they will annotate that typically with an asterisk. I think that's what I've seen typically. And it's a good visual indicator of the relationship because sometimes the numbers will seem interesting, right? When you take a look at them in an article, you're like, that doesn't make sense, right? But the statistical analysis that's happening behind the scenes that's dictating the strength in that relationship will show you kind of this graphic depiction. Typically, that's with an asterisk. Okay, 1, 2, 3, or none. So if I have no asterisks, then, and we'll see some of that in some of our use cases this evening. If I don't see any significance, then I'm, visually I can see that very quickly with no asterisks. So that's why we have it. All right. Any questions on this model? Pretty simple. That's why we call it a simple linear regression. But it's really about the fundamentals and kind of reinforcing what we've discussed thus far. That's all it is. Okay. All right, so let's add a couple notes, right? Keep us calibrated so when we go back. So this BH mod, so what we wanted to do here, we'll just drop that down here. So we'll throw in our hashtag to make sure we don't run it. And we just wanted to print the summary essentially to the console. And then here, we'll just add a little note under here is that all we did here was we conducted or ran the regression, right? Simple. So now I know when I go back and I look at this, and I can just hop back here and tell you exactly what I did. Good stuff? All right, everybody good online? I'm probably getting way too close to this, this camera. All right. So if everybody's good, let's go ahead and draw a line, right? Kind of like a page break, and then we'll kind of move into kind of the next scenario, okay? All right, so here we go. So on to the next objective. We're going to go back to the slide. So you're going to see we're going to start to build the fundamentals, all right? So we talked about linear regression. We talked about how linear is different from multiple regression and introducing additional constructs, or i.e. x1, 2, 3, 4 independent variables. They all mean the same thing, regressors, if you will. So now we need to build upon this simple, regression model and kind of step into the space and play with multiple regression. All right, so we're going to keep building on the fundamentals. All right, so let's rock and roll. So let's go back to the PowerPoint just briefly. So good job on the first exercise, but let's go a little bit deeper, okay? So now we're going to kind of look at some of the uniqueness and the descriptions of the variables within this Boston data set. Which variable would you expect to have the highest p-value? We just talked about that, right? We talked about asterisks, identifying significance, right? I can say that I'm 90% confident. I'm 97 or 99% confident that this relationship exists. So which variable would you expect to have the highest p-value, now that we have a good understanding or we're calibrated around that item, in a multiple regression model which uses all remaining variables as regressors to explain median value? So we could go back into our studio, right? And if we wanted to take a look at, our Boston, so if you just click on Boston real quick, right, we've got 506 data points in there. But what you'll notice is high level, you've got all your variables at the top, right? Not all of them are spelled out, but you kind of get the picture here, right? So there's a variety of different variables here. Everybody see them at the top? They're kind of highlighted. So there's our median home value. Here's our socioeconomic status. Here's taxes. Here's age, disability, industry, zone, and crime. So just looking, if you were to just take a wild guess, just, I'm gonna go out on a limb, right? Which one of these variables do you think has the most significant effect on median home values? If you're just gonna pick one. This is your chance to guess. All right, we got to click. Did somebody place a wager in the chat room? What's that?
Dr. Megan.
Okay. All right, so just choose one, somebody. Just, what do you think has the greatest impact on median home value? Just guess. Huh? Crime? Taxes. All right. So if we want to look at crimes and taxes, right, we've got to maybe look at a different type of regression model, right? So now I'm looking at how much of the variance can I explain, or how much variance, or how much can I explain with confidence of each one of these independent variables and understanding how they impact that dependent variable. So to do that, we've got to do a little bit of multiple regression, right? Because now I've got multiple independent variables and I need to understand how that affects the relationship. So if we go back to Untitled 2 or whatever you have, say, hopefully you saved it something other than that, we need to start to take a look at that, all right? So we want to obtain some coefficients first, right? Look at robustness. So to do that, we're going to inject a little bit of code here. All right, so here we go. Fingers on the keyboard and go. Mod, right? So we're going to go mod. Then we're going to introduce our sign. Okay. Let's open up those parentheses. And you know what? Let's look at that median home value. Oops. Let's tilde. Okay, and tilde means what in the context of code? It's the funny little key that nobody ever uses or knows what it's called. It's the regression. All right, so we got to put that in there because we need to tell it to do a regression model. All right. And then let's look at a couple different variables, right? So let's loop back in our socioeconomic status, right, which was LSTAT. Some folks mentioned crime, so we're gonna throw that in the model. Get a little space here to keep it clean, right? So crime is kind of that nomenclature for what we saw when we looked at the different variables. All right, let's look at age as well. What do you guys think about that? See what happens there. Do we think age might impact median home values in the suburbs of Boston? I don't know. We're going to find out though, right? So then we got to tell it what data set to look at, right? So we said, hey, we want to do some regression. We want to look at these variables, but then we got to tell it in R which data set to pull or run that model, right? So the model for us is data. Everybody remember? Data equals what? Boston. Simple. Okay. Everybody good? So let's do this. Scroll down a little bit for the folks at home. We'll go ahead and highlight. So click on your, your left pane, highlight, and go ahead and run. All right, so notice we moved the data, right, that ID of mod, over to the environment. So you see it? Everybody see it? So we've got to move it over. All right, so if everybody's good, we're going to kind of run that coefficient test again, right? So remember the code that we did in the first section in the first problem? We're going to rinse and repeat that. So everybody follow me. So we're going to go down here. Remember, coefficient test. I'm going to grab it from the auto population here. And then we're going to do mod. So mod is going to pick it up from our environment. Everybody see it? So we got to go pick it up. So now we've brought it in. And then here we're going to do that VCOV, right? Otherwise we can't look for robustness or standard error. Right? Everybody with me? And it's the dot equals, same equation. And then we do what next? Remember, VCOV, HC. Good. And then we can get rid of some of this. That looks good to me. Everybody good? All right. Now let's create some statistical magic. All right. So here we are. Now we've got more things, more items introduced to this model. So we just talked about what's over here, right? In the previous model, that linear regression, we had one independent variable, right? That we were regressing against median home value in our data set of Boston housing, right? But we said, hey, taxes. We said, hey, crime. Somebody said age. So let's bring that into this model, kind of run a multiple regression, and let's truly see if there's a relationship that exists. So the first thing we can do is look at our estimates. So what are our estimates telling us here? We've got low socioeconomic status. Is that consistent with what we've seen in the linear regression model that we just ran? Right? We kind of have this inverse relationship between median home value and socioeconomic status, right? But what you'll notice here is if I scroll up just a little bit, we've brought more regressors into the model, right? So we're explaining the variance of these different independent variables on our dependent variable. So the strength of this relationship of socioeconomic status will naturally what? Could decrease or increase, right? Because I've introduced more variables into the equation. So if we just look up here for argument's sake, right? You see your estimate here of negative 0.9, right? And here, pretty consistent, right? So we're seeing the kind of the same story here is the point. Okay? So we're seeing some consistency. Now we have crime. We bring in crime. And I know somebody brought that up here in the class. And we also see a relationship here. But what's interesting is kind of what is the story telling us about that significance out here, right? It's a little bit different. If we look here, we can say that that inverse relationship that was very consistent with our linear regression model is still consistent when I added these additional variables into the mix, right? And it's still highly significant at the 0.001 level, right? So pretty consistent so far. But then you guys said, hey, crime's a problem, and we see that there's going to be some sort of relationship between crime and median home values, right? Were you right? Yes. You should give yourself a round of applause. But you were right, right? You were right. But we confirmed that with data, and we confirmed that with statistics. Because nobody's going to believe you until you show them with data, right? So here, I can come to the conclusion that there is this inverse, right? This relationship between crime, right? So as crime decreases, right, what happens to the home values? They increase. Does that make logical sense? Does it pass the smell test? I think so. But tell me about age. What's going on over here? So we have a positive, right, relationship on our estimate. We see that here, right? So we've regressed age into this mix. So does age, if age increases, like if we see an increase in age, or do we see any sort of impact to median home values? Maybe, right? But what's this telling us about that relationship, the strength, right? The significance. What's our asterisk telling us? Right? You see our legend here, we talked about that. Right? So it's a 95%, I'm 95% confident, right? That relationship exists. That I can explain that relationship by looking at the impact of age on median home value in the Boston suburbs. Housing. Right? So our model is telling us what? That these independent variables do in fact can explain the variance or the variation or impact the output, which is the home value, right? So we can say statistically, because it's significant, that both socioeconomic status, crime, and age all influence, or they can be used as predictors of median home values in Boston. It's that simple, folks, right? And the statistics told us that. That's all it's telling us. It's telling us a story. And it makes sense, right? We kind of walk through each one of those relationships. Okay? Any questions? Because this is getting really magical, real fast. Any questions at all? No? There'll be a 10-question quiz at the end of this block, so we'll see. Can you help me write a quiz? But yeah. All right. So I think it might be time for maybe just a quick 3-minute break. I know we've been kind of working through this and progressing. So let's relax our brains, I think, for 3 minutes. Take your hands off the keyboard, maybe run to the restroom, grab some water, and 3 minutes. So let's start back at 33 after. Does that work for everybody? All right, awesome. And then we'll jump right back in. 3 minutes for the folks at home. That makes sense, maybe. You guys able to follow along with this stuff? Okay? Yeah? Let's see what's going on in this chat room here. It seems to be pretty active. All right. Need to zoom out. See the whole thing. We only see the top console. Hopefully you guys, Kathy and company, can see the console. Age, good. think the question is from Robert. So we haven't run income yet to see if there's any sort of multicollinearity. There are also tests of multicollinearity that we can run that will tell us that, which I don't think we'll get to that today. So sorry, I know that doesn't answer your question, but we are going to run a multiple regression against all of the independent variables in the Boston data set. So we'll see if we can identify any of that to the eye on the initial poll. So we're going to jump right into that here in a second. Which sports do you guys play?
The rowing team.
Oh, cool.
I used to row.
Yeah? Yeah. I tried that once in the YMCA, but it was only once. Yeah. Never did that again. Canoeing? No. Currents? Not interested. All right, awesome. So, ladies and gentlemen, I added a few notes again, so you can go back and revisit just to explain kind of what we did. So, if you want to just take a couple seconds and jot those down, and then go ahead and separate do your page break with a sequence of counts, and then what we're going to do is we looked at some of the variables that we thought would have some sort of impact, right? So now we're going to look at all of the independent variables and kind of pull them all in and take a look. Okay, everybody good on the notes? So let's jump back to the good old PowerPoint, or briefly. So now we're going to do the real McCoy, right? This is where it gets exciting. We're going to pull in a lot of independent variables. I'm trying to hype it up. You guys got to help me, right? I'm trying to hype it up. So we're going to take a look at a variety of different. You saw how many variables were in this Boston data set, right? All right. So let's make some magic here. So
you want to do one thing, do question mark Boston.
Yeah, for sure.
And then it'll pop up in the help section, and then you can see what all those variables are.
Yeah, for sure. Oop. Nope. There we go. Here we go.
And then it explains what each variable is.
Okay. Perfect. Did you guys run that? So housing values in the suburbs. So here is our variables and their descriptions. Okay. So the help function is actually very, well, this is going to seem very cliche, but it's very helpful, as you can imagine. But there's a lot of different things you can do with the help function, believe it or not. So we have crime, which is per capita crime rate by town. ZN, which is the proportion of residential land zone lots over 25,000 square feet. Retail, the Charles. So there's a dummy variable. Have you guys used dummy variables? Done any work on that? Okay. NOx, nitrogen oxides concentration. That sounds interesting. RM, average number of room dwelling, right? Since we're looking at suburbs, that makes sense. Age, proportion of owner-occupied units built prior to 1940. A lot of old real estate in Boston. Weighted mean of distances to 5 Boston employment centers. I was way off in my interpretation of what dis meant initially. And then RAD is the index of accessibility in radial highways. Tax, full value property tax, per 10,000. PT ratio, people teacher ratio by town. Proportion of blacks by town, which is black. We talked about lower status of the population, right, or lower economic, socioeconomic status. And then MEDV is that median value, okay, of owner-occupied homes. So that's the description of our variables, and then it gives us our source file, right? So if we want to go research, where this came from, we just scroll down here, and we could Google Scholar, we could use Swisher, we could find these sources and verify that they are legitimate secondary data sources. Okay, everybody good? All right, so we'll just jump down here. Question mark indicates help within the viewer, right? So now if you need to ever do anything, you want to understand one of your values that are over here in your environment, and you just add a question mark, and then it's immediately from a code perspective going to pull you into the help box. All right, so let's jump back over here. So again, we're doing the holy grail here. So regress that MEDVB variable on all remaining variables that you find in the Boston data set. So we just went through like each one of them. I think there's 12, if I'm not mistaken. There you go. See, that was a check on learning. Let me pass. So now we're going to pull all these into a multiple regression, and then we're going to look at the summary statistics, coefficients, same thing that we've been doing thus far. But now we're going to look at the entire Boston data set. So obtain a heteroscedasticity robust summary of the coefficients. Say that 5 times, right? So we're going to take a look at that, and that's going to be indicative of the code that we enter into R. All right. So we're gonna go through that exercise. All right, everybody ready to go? All right, let's rock and roll. So first order of business, we're gonna do something like this. We're gonna go full underscore mod, right? Because we're running the holy grail here. This is gonna be magical, I promise. All right, let's throw in our sign. Right? What's next? Remember, we want to run this regression. We've done it 3 times so far. There you go. Okay, walk me through it. LM. That's right, because we're going to regress against that. So MED, V, tilde, that's the sign that nobody ever uses, right? Also known as the regression tilde, right? And what do we want to do here? Because we want to look at everything. This is the moment, folks, that we've all been waiting for. So to do this, we're going to simply just enter a character, all right? So we're going to enter a period here. And basically what we're telling R is we want everything included in this model, okay? And we want to regress those independent variables against the MEDV. Everybody good so far? So then we've got to, let's just throw a space in here. You don't have to. Let's just go comma, right? Because now we need to say, hey, I want to run this massive holy grail of a multiple regression model. I'm going to throw in that tilde. Now I need to pull it out of the data set, right? Everybody good? So we got to pull it out of the data set. Which data set are we using? Right? So then what do we do? You guys are on it. All right, so data, do we let it populate? Yes, because otherwise we'll mess it up 90% of the time. Then we'll click data equals what? Is it case sensitive? Yep. So capital B, OSTON. And are we done? Not a trick question. Perfect. Let's give it a shot. All right, everybody highlight your line of code. All right. Now we brought it over. Everybody see it? Because we classified that model as what? Full underscore mod. So we had to make sure it went over to the, where am I at? Global environment. Everybody see it? right? So we're good. We got no errors downstairs in the console, right? No errors. So now what we've got to do is kind of rinse and repeat, like that coefficient test kind of string. So let's do that. But before we do that, let's just add a couple notes here, because when you go back, you're probably going to want to remember how you ran this model. So we'll just say run a regression of, and we'll say which variable, right? On all, remember this is the holy grail, remaining variables in the Boston data set, right? That's what we did, right? We just said, hey, I want to run this massive regression model, and I want to include all the variables in the data set of Boston, right? Easy. All right, so let's jump back in. So now we want to do what? That coefficient, yep, coefficient test. Highlight and click. There you go. And we are cruising now. So full underscore mod, we'll let it highlight, right? Click it. Full mod. Then we go comma space. There you go. Bcov. Then we're going to make sure we click it. And we're going to make a small adjustment here. So we're going to do something different. So we're going to go, let's go with type. All right. Space equal space instead of data this time. Let's see what this does here. Everybody good? We got it? All right, ready to create statistical magic? You know the drill. Let's run it. And there we go. Look at this, ladies and gentlemen. We have arrived. No, still not fired up about regression. All right. So let's take like 2 steps back, because we need to just talk about what we just did, right? So what did we just do? What did we just tell R to do? Because coding language is just weird, right? But what did we just tell it to do? Like, it's just like Excel. Excel just doesn't do things for you. You don't just open it up and you're like, hey, Excel, run me a regression. I mean, that would be cool. But it doesn't do that, right? You have to tell Excel to do something for you, right? And you do that through formulas. So same thing here. It's just coding. It's just another language. You guys will actually be bilingual in R by the time you graduate Dr. Davis's class. You don't know it, but you will. So what do we tell R to do?
Regress median home value against all of the other variables.
It's that easy, right? That's all we told it to do, right? And what did we get? Exactly that, right? So let's take a look over here. Notice.
We couldn't hear that online. Could you repeat?
Oh, of course. Yeah. All right. Try not to make this awkward. Can you hear me now?
Yeah, just lost you when he said what we told it to do exactly.
Oh, I think the next class I'll request a wireless mic, a lapel mic. So thank you for calling that out. All right. So I was just kind of walking through like this progression to where we are now with kind of the holy grail of regression models, right? So the explanation is rather simple. So this is what we're telling R to do is essentially what we've asked it to do, right? We said, hey, we want to look at what is the impact of all of the independent variables inside of this Boston data set, and how do those impact or explain or predict our outcome, right? Which here is the median home value for the Boston suburb data. So we were just, for the folks at home, we were just kind of recapping just in simple terms, right? Because we need to, when we're dealing with this stuff, we need to keep things simple and keep it real. And to do that, we've got to explain it in simple terms. And that's exactly what we've done here. So we were just kind of recapping, like, what did we actually just tell R to do? And one of the students in the class did a really good job of articulating that. And that's all we did is we essentially told R that we wanted to understand what the relationships are with the independent variables or all these different variables within the Boston data set that we've been working with since the beginning of these exercises, and how they regress, or what does it look like when we pull in that median home value dependent variable. So that's what you see now in the console, right? So that's hopefully you heard all of that.
Yes, that I thought maybe we were figuring out why we use type equal HC1. Is that just another way of getting us the cove HC?
That's correct. And
Okay,
then, go ahead, Dr.
Yeah, there's
Davis.
several.
Yeah,
different
I like
ways-
coding, so I ask those kind of questions.
Perfect.
There's
Good.
several ways you can run robust standard errors, and HC1 is just one of those robust standard errors.
All right, great question. All right, cool. So I'm assuming maybe if I walk over here, I turn this.
Yeah.
All right. Can you guys see the screen in the room? I mean, I'm sharing it as well, so but I'm gonna walk over there. This is good? All right. Silence, acceptance. I'm gonna move forward. All right. So over here on the left side, we have what? Independent variables, right? X1, X2, X3, X4, X5, X6, right? All the independent variables. And what are we trying to understand about these independent variables? Can they explain, right? What? Talking about regression, right? So we're regressing these items, right? These variables against what? Right, very good. And we've been doing that in every one of these exercises, all right? So we're back there again. Good. So let's talk about some of these. Let's start with the no relationship at all story. All right? So with confidence, what are some of the things that just have no correlation to our dependent variable, median home values? Where do we see no impact? Okay, good. How do you know that? There we go. It's back to the asterisk conversation, right? So easy visual identification. Good. What else? Age. Did we see that in the other model? No? Interesting.
One asterisk on the model.
Right? See it? Good. It was one asterisk. Well, that's kind of funny. How did it have an impact before, but now it doesn't? Because it was adjusted. Okay, that's a good way to put it. Does it have anything to do with us introducing more noise into the model? And by more noise, I'm talking about more stuff. More stuff, I mean more variables. More variables, i.e. your X1, your independent variables, right? Good. So we're starting to see some of the variance kind of shift, right? It's telling us a little bit of a different story. We knew that it was kind of, I mean, 0.05 is a pretty decent, level of significance. But as I introduced all of these additional variables and regress them, right, and this massive holy grail regression model, we no longer see that, right? And that's okay, because the intent of this exercise is to truly understand if I were to bring in all those variables, what does it look like? So let's go back down here. What else? What else is unique about this model? Did we see a similar relationship that we saw previously when somebody said, hey, look at crime. Crime's a problem, right? Crime per capita is going to impact median home values in Boston. Do we see a similar story here?
Not as much,
Right? And again, why might that be?
because there's a lot of other factors.
There you go, right? There's a lot of other factors. And we talked about that at the very beginning of the presentation, as you can recall. So typically there will be more than one factor that we need to take into account to understand truly what's driving the relationship. Good. You've got a lot of things that are highly significant, right? Statistically significant at the 0.001, right? That's a pretty strong relationship, right? So can we confidently say there's a relationship between some of those items, some of those constructs, those variables, and how that might change or predict your output for median home values? I think it's a resounding yes, right? So that's indicative of what you're seeing here, over here on the right side, right? So we've got a lot of predictors here that we can confidently say impact our model, i.e. impact our output to which we're measuring. Now, could we have taken median home value out and put taxes or socioeconomic status as that dependent variable? Sure. Would that change the relationship of what we're seeing? Yeah, because we're looking now at a totally different relationship. So you're not going to see similar relationships. So if you move different types of variables around, you will in essence see different estimates, you'll see different statistics. It'll tell you a variety of different things. But for this particular use case, what we were trying to understand was median home values.
So looking at it, it's not really looking at the different outputs. So like what were the top three, what would say is confidence in top three factors?
Yeah, that's a great question. So if you were going to pull out, and really the story you're trying to tell here, and Dr. Davis, of course, chime in, is that you have statistically proven that there is a high level of significance at the 0.001 level between these variables, right, that you see here that you've identified, that can help us explain or predict that home value, that median home value variable. And of course, the strength of that significance is very, very important, right? So if you were going to write about these relationships, you would write about them in a similar way. Because even though some of the estimates may be a little bit different, your level of significance is really, really important here, right? Because you're saying with a certain level of confidence that this relationship exists. And please add to that.
Yeah. Another thing we'll get to in future class is tuning the model so you can drop out non-significant variables and see how the coefficients continue to change. There's also stepwise regression where you slowly add in the variables to see how they change. But with this example, another key point though is LSTAT, the first variable that we pulled in. Look at how much it changed. It was negative 0.9, and now it's negative 0.5. So the magnitude of that coefficient has dropped in half.
Yep.
And that's due to something that's we started with omitted variable bias. Because we weren't adding in all these other important variables, we see that we were over inflating the value of that effect of that variable. And you can see the different magnitudes based on the size of their coefficient, how it's going to affect that dependent variable.
So would you say, like looking at black would be 9.3? That's the highest positive.
It's 9.3 times 10 to the negative third, so it's actually 0.0009. So it's actually not as.
I see this. The LSTAT is 0.01.
Yeah. And we'll see
Here.
It's like rooms and 0.0.
I think PT ratio is 0.9.
Yep.
That might actually be the one with the highest magnitude.
This is a pretty good model. Like this is some pretty good results to have when you run these types of models. And then as Dr. Davis mentioned, there's a variety of different ways to approach modeling, especially depending on the type of data, right, that you're collecting. There's a model for your type, whether it's ordinal, whether it's nominal. That might be outside the scope of this class. Like for an example, we wrote a summer paper this last summer, and what we looked at is civic perception of autonomous vehicles in a public transit ecosystem, right? And to do that, we introduced a survey, right? We wrote items based on the technology acceptance model, which looks at perceived usefulness and perceived ease of use. We looked at trust. We looked at something called SAE, which is Society of Automobiles and Engineering, levels of autonomy. Is there a driver there or not? So we tried to understand what that impact was on the likelihood that a consumer would leverage an autonomous vehicle as a public transportation mode. Makes sense, right? Like how would people perceive that? So our approach, regression, based on the data that we were collecting, is probably may not be the most proven approach. So we looked at what we call an exploratory factor analysis and a confirmatory factor analysis. And what this does is it allows us to look at the data from a very unique perspective, and we call it kind of load factors, right? How do the different variables load onto the dependent variable? So there are multiple ways to kind of look and organize your data based on the data that you're collecting. But truly, this is going to tell us a pretty good story of what these relationships are and how they exist. And that's really the takeaway from this model. But I give you that example, that just brief example, that there's some very complex, modeling that you can do that may in fact tell you a different story. Okay, cool. So we should probably add a couple notes in here. So here we kind of, let's see. Maybe that works. Right? So we did some work there. And then somebody said, well, what about the R square, right? We got to do an adjusted R squared, right? Like what, why? Why do we got to adjust it? Right? Because we're not looking at that linear regression, right? So we've got to account for the introduction of the model of those additional regressors. Very good. So we want to take a look at that? All right. So here we go. So let's do this. Let's try summary. All right. And then let's insert the object. So we already brought full mod over, right? Everybody remember we brought that over to the global environment? So now we need to do a little bit of coding, which should be somewhere in this neighborhood, to get the R squared. So summary, we're going to pull in that full mod from our data, from the global environment back in, and then we're going to introduce this additional line of code to understand what the adjusted R squared is. All right? Everybody good? All right, so let's run that and see what happens. So what is this adjusted R squared telling us? Can you say that a little bit louder?
I think it means that 73% of the variability is explained by the model.
Very good. Very good, right? 73, what, 0.3%? 4%? Right? So we're essentially converting that into a percentage of variance. Very good. Any questions online or in the chat? I haven't checked the chat, Dr. D. Good. Yes, sir.
I got null.
You got null? Let me take a look. All right, we're back in business. All right, so I just want to do a very quick recap, all right, on what we've discussed thus far. So in the beginning, I told you about myself, which was born, right? Everybody remember that? All right, good. But on a serious note, we kind of talked about kind of like opening up the vignette, right? Kind of us stepping into the sandbox of regression, building upon what you've already done in chapters 1 through, I think you're at 5 now, so this was 6 and 7 or something like that, right? So we've kind of just been building the foundation to where we are today with regression. This all relates back to your terminal learning objectives and what your, Dr. Davis has set out in your syllabus for you guys to learn in this course, right? So all we're doing is just continuing to build. Through that, we talked about the differences, like what's the difference between a linear regression model, multiple regression, where we introduce additional independent variables. We talked about coefficients, right, briefly, and then took a look at them statistically. Then we played in this world called fit, right? So we wanted to understand kind of how our data kind of measured up in terms of fitness to that line, that regression line. Multicollinearity came up, right? Big fancy word, ends with a Y, right? Which allows us to understand if there's a relationship between the independent variables. And then we said, hey, well, if we see that, right, that's going to impact our results in our model, so we got to do something about it. So we talked about some ways to take care of that. And then we kind of jumped into some of these, a series of exercises. So we took what we learned at the very beginning of the course today, right? We kind of built the fundamentals. We talked about some pretty boring formulas. And then we took all of that and put it into practice. And that's where the learning happens, right? So hopefully you saw us bridge the gap between what we learned in the PowerPoint and kind of through kind of the broad discussion, and then took all of that knowledge and put it into practice. That was the intent of that first module. Okay? Any questions so far? All right. Just doing that good of a job, huh? All right. Self-fulfilling prophecies. Go ahead and make sure you hit save and on.
Does this thing like assignment?
This is for, so we won't do any more R, I think, in the next block is relative, because it's a hypothesis testing, so I don't think we do any R work in this next chapter. So
yeah, just save it as assignment 3, the .r data and the .r, and you can turn that in.
for the folks online, I'll go ahead and do this whole camera thing again. So I apologize if you're looking at my forehead or the top of my head, but go ahead and save this as assignment 3 in your .r file, because this will conclude the R portion. You guys get that online? You good? Hopefully the audio is still working. Can't see the chat. Take a check.
That's what you want us to upload.
We got it. Thanks.
Ah, perfect. Thank you. All right. All right. So I'm not going to bore you with too much PowerPoint. Usually have a 10-slide limit. So we're going to cruise through here, right? But this is important, right? Because this next, kind of brief block should last just about 2.5 hours. Come on. But it's important, right? It's an important topic, right? We talk about hypothesis testing, right? Everybody has a hypothesis, right? Everybody has a unique way of how they see the world. So when we do research, right, we're trying to understand statistically if a relationship exists. Was there a comment? No? Oh, okay. We're trying to understand and test to see what we believe. So some of you, let's just go back, right? Some of you said it's crime, right? Or it's age, right? But then we statistically ran a model to understand if that relationship truly exists, right? So essentially what you were doing was creating a hypothesis, right? At that point, you were saying that there will be some sort of positive correlation, between some variable X and Y, right? And we took a look at those. So you're creating some of those preliminary hypotheses. Those hypotheses may be rooted in theory, right? In academia, theory is what we build upon, right? In terms of the body of knowledge. So that's essentially what we're doing here as well. So we're going to talk about just briefly a few topics, right? Kind of play in the hypothesis space a little bit, talk about confidence intervals. You learn more about that kind of in advanced statistics. But it's important because it's really specific to your sample and the data that you collect and kind of where all of that falls. All right, so let's rock and roll. So we talked about p-values, okay? We talked about those, and then we talked about a t-statistic here shortly. But what's important here is, again, we have to have a way to test our hypothesis, right? And can you have multiple hypotheses? Yeah, is there any like limit? Is there any law that says, hey, you can only have one? No, right? You can have multiple hypotheses, right? It can get a little messy if you do, right? Depending on how many you have. But you can have multiple hypotheses. Then we have this idea of a null hypothesis, right? What is a null hypothesis? I mean, you got a null value back there, so maybe has nothing
There is
to
no
that,
relationship.
right? Just nothing, it just remains unchanged, right? Stay the course. So when we introduce a hypothesis outside of the null hypothesis, it's what? It's an alternative, right? It's an alternative hypothesis. And now you have multiple alternative hypotheses. So we've got to have a way to test those, and we can do that statistically. So this kind of brings us to confidence intervals. So to caveat, I am not an artist and I do not play one on TV. So no laughing from the crowd, but this is a bell curve, right? A normal curve. When we look at kind of the shape of the top of the bell curve, we look at kind of what we call skewness or kurtosis. That tells us some other things as well. But for the purposes of this, in some statistic classes that you may have while you're at JU, you'll manually do this. Another painful effort, but it's important that you understand that. So real quick, right? Here's kind of your mean population, right, for your sample. I know it's hard for you guys to see. It's just an X with a bar on top, right? Or you could have a population mean, which is U bar, right, Dr. Davis? Population mean, U bar, X bar, same thing, right? We're just talking about the population mean. Here you have standard deviations, right? So you guys have heard that. It's like, hey, I'm one standard deviation away from the mean. Everybody's there, right? You have a positive and a negative side of that. And then what you have is these confidence intervals, right? So we were talking about 95% confident, right? We're talking about 99.7, right? That 0.001. So all we're really saying here with a level of confidence is where our data and our samples fall, right? So when we take our data, we collect it, and we look at the distribution of our data, it's going to fall somewhere in there, right? So the question is, you know, where does it fall? So if you look at the normal bell curve, you have like 68% of your data is going to fall like kind of within this area. And that could be left of the mean, negative, or right of the mean, positive, right? So somewhere in that area. As you push further out on the bell curve and you further disperse your data, right, then you're capturing kind of 95%. So it takes that kurtosis, it pushes you outside the box of 68.3%, right? And now you're capturing that 95.5% confidence interval. All right? And then when you push out further, they call these the tails, right? Tails of the bell curve. And then you're capturing the entire bell curve. You're plus or minus 3 standard deviations from the mean, right? So pushing out towards the tails, which is roughly 99.7%. But this is important because you'll see kind of the correlation between what we're talking about here, how your data looks, right, when you collect it, and how it kind of impacts your overall modeling. So important stuff. We talked about that. It's what I attempted to draw for you on the whiteboard. That didn't go too well, but here you have it. So the F statistic. So I think I was going to go here. Sorry. So the confidence sets. This is what they call a multi-dimensional generalization of a confidence interval. You're like, wow, that's a lot of words, right? So this is a kind of set of points so you can kind of see this predetermined point, and what it's doing is providing an ellipsoid, kind of a generalization of your data in somewhat of a different context here that's represented by this ellipsoid that you see here around a given point. So the point of this is there's really kind of different ways to depict the coefficients. I have never used this approach. I don't know if you've used this approach, Dr. Davis. But again, this is just exposure to, there are a variety of different approaches and ways you can graphically depict confidence sets, and then specifically for multiple coefficients. And then kind of taking a look at, let's just use test score data. So these are kind of a variety of different use cases. And you can see there's 5 different model equations, right? So based on what we've learned thus far, we've got this idea of a test score, right? And then we've got these other variables. We've got size, English, lunch, CalWorks, right? All of these other different variables. So we're kind of building out that regression, if you will. And then this is kind of pieced together, so I apologize if it's difficult to see. But let's talk about some of those things. What are some of the first things that kind of are glaring at you? When we look at your dependent variable, it's test score. So again, we have these independent variables, right? We're not going to define them. I don't remember what they are. But we know that there's some sort of impact, right? Or they're driving some sort of effect on test scores, right? So what are some things that are glaring? Right? I see some asterisks up there. So I know there's something that's happening in that first model with regards to size, right? Size influences test scores. Does that make sense? If I have a class of 500 or a class of 5, do you think the impact on test scores would be different? Yeah, probably, right? Smaller class size, smaller ratio for teacher to student. Yeah, English, lunch, right? You could see kind of the statistical significance represented again by that asterisk up there. So this is, again, we're not going to go through each one of these, but this is reinforcing kind of what you've seen so far in the different models. All right. Here's our adjusted R squared. Everybody see it? So the student in the front kind of mentioned that 77.3%, right? Explanation in that model. 62, 77, right? So we're seeing that and converting that decimal into a percentage, right? Which is the percentage of explained variance. And we talked about that. And those are the major items that I think we just needed to cover based on what we covered with multiple regression. So this just kind of puts it in context, just kind of reinforcing what we did with the Boston housing data and looked at that Holy Grail model. We said, okay, well, let's go look at that again. And this is just kind of one of the predisposed models, okay? Any questions? No questions at all. Have you guys had dinner yet? That's an important question. Is it dinner time? Yeah? All right. Well, after the 35 question multiple choice and thing like this. So that concludes the 2 blocks of instruction. I just want to thank you guys for your participation. And I hope you do truly understand how this is going to impact you later in life with some of the things that you do, as it has mine. Everything that you're learning here in the schoolhouse will become applicable if you make a concerted effort to make it applicable, right? That's how it works. So what you're doing in this class and what Dr. Davis is teaching you will not go untold. You will find yourself looking at this stuff in some sort of unique way when you get out of JU, for sure. So I wish you nothing but success in your future endeavors, your future rowing events. But I hope that you guys do very well in the rest of your studies. You have my card and my contact information if you're interested in internships or what have you, or jobs when you come out of here. Then just keep my contact information and be more than happy to connect. But I thank you, and I thank everybody online. Thank you very much.
Thank you.
Thank you. Yeah, and I guess Dr. Davis, if you have any closing remarks for the class, for your classwork.
Okay.